Everything we know about the universe is just a tiny fragment of a grand mystery. Myriads of stars, galaxies stretching billions of light years, are just the tip of the iceberg. Beyond our understanding, beyond the event horizon, lie unexplored worlds and phenomena that could overturn our concepts of the cosmos. Every new mission, every telescope launch is a step into the unknown, revealing ever more secrets. But what if what we see is just an illusion? What if beyond the visible boundary lies something so grand and incomprehensible that our minds are simply not prepared to grasp it? The latest breakthroughs suggest we may have only scratched the surface. Liking this video helps us share these discoveries with more curious minds, and subscribing ensures you'll never miss a chance to explore the universe's secrets alongside us. We embark on a journey where the answers may be even more mysterious than the questions. What secrets lie beyond the universe we know? Could there be another reality, different laws of physics, other forms of life? Are we ready for discoveries that could change our understanding of time and space? What truly lies behind the veil of cosmic unknowns? If you're as intrigued by these questions as we are, make sure to hit like and subscribe to our channel. Join us as we venture into the mysteries of the universe and uncover what lies beyond the stars. Our universe is an immense space filled with mysteries and wonders. It emerged as a result of the self-evolution of matter, specifically due to fluctuations in the inflaton field. Its vastness is awe-inspiring and evokes reverence in anyone trying to grasp its scale. Understanding the scale of the universe is the first and most crucial dive into cosmic space, giving us insight into how small our world is compared to the boundless expanse of the cosmos. According to calculations by an international team of scientists, our universe is expected to last at least another 140 billion years. The observable universe stretches about 93 billion light-years in diameter. This distance is almost impossible to conceive, as 1 light-year is the distance light travels in 1 Earth year at a speed of 299,792 kilometers per second. In more familiar terms, this is roughly 9.46 trillion kilometers. Interestingly, most of this vast space is filled with emptiness, with sparse islands of matter such as galaxies, stars, and planets. Despite its colossal size, the observable universe is only a part of a broader reality that science has yet to fully understand. Currently, scientists estimate that the universe contains about 2 trillion galaxies and around 10 circumflex 24 stars, more than the number of grains of sand on all the beaches on Earth. These immense scales not only inspire awe, but also pose many questions. How did the universe become what it is today? What lies beyond the observable part? At what scale might we discover new physical laws or even parallel universes? Galaxies, the fundamental building blocks of the universe, are distributed across space in complex and diverse structures. Their arrangement is not random and follows specific laws, forming the large-scale structure of the universe. They have a spherical shape and contain tens of thousands of galaxies, usually elliptical or lenticular in form. At the center are 1 or 2 giant elliptical star systems. One of the most remarkable aspects of this arrangement is the existence of large cosmic voids. A major void can stretch over hundreds of millions of light-years and contain extremely low galaxy density. With a diameter of about 330 million light-years, it is one of the largest and most well-known in the cosmos. The distribution of stellar systems across space forms grand and complex structures, which are key components of the large-scale universe. Recent research by Estonian astrophysicists Y. Einasto, A. Saar, M. Yivar, and others, as well as American specialists P. Peebles, O. Gregory, and L. Thompson, has shown that the largest scale inhomogeneities in the distribution of galaxies exhibit a cellular structure. The walls of these cells contain many galaxies and raise questions about the nature and other fundamental aspects of the universe that require further research and observation. So in which cosmic structure is our home galaxy, the Milky Way, located? The local group of galaxies is a small cluster that contains our Milky Way. This cosmic ensemble includes over 54 galaxies within a radius of about 10 million light-years. The main members of the local group are 3 large spiral galaxies: the Milky Way, Andromeda, and Triangulum, or M33. The Milky Way, with a diameter of about 100,000 light-years, is one of the most massive in this group. It contains approximately 400 billion stars, numerous planetary systems, and other cosmic objects such as nebulae and star clusters. Our nearest neighbors are the dwarf galaxy in the Large Magellanic Cloud and in the Small Magellanic Cloud, located about 25,000 and 200,000 light-years away respectively. Andromeda, M31, is the largest galaxy in the local group. It is located approximately 2.5 million light-years from the Milky Way and has a diameter of about 220,000 light-years. Andromeda contains around 1 trillion stars, making it the largest member of our local cosmic environment. In the future, in about 4.5 billion years, Andromeda and the Milky Way are expected to collide and merge, forming a new stellar system. An interesting aspect of the local group is the Triangulum Galaxy, M33, which is about 3 million light-years from Earth and has a diameter of around 60,000 light-years. M33, with a population of 40 billion stars, is also a spiral galaxy, but smaller compared to the Milky Way and Andromeda. This group also includes many dwarf star systems, such as the Leo 1 dwarf galaxy and the Sculptor dwarf galaxy. They generally have a diameter of less than 10,000 light-years and contain far fewer stars compared to the larger members of the group. Many of them orbit around more massive galaxies, acting as their satellites. A central question in this cosmic group is what lies within the cores of these galaxies? Could there be black holes significantly more massive than our Sun at their centers? These are questions that drive further research and new experiments. Interactions between galaxies in the local group occur under the influence of gravitational forces. Such interactions can lead to the exchange of material, the formation of new star systems, and even mergers. An example of such interaction is the dwarf galaxy M32, a satellite of Andromeda, which shows signs of tidal effects from its larger neighbor. As a small part of the cosmic web, this group serves as a unique laboratory for studying the evolution of galaxies and their interactions. Studying them helps astronomers better understand processes occurring on the scale of the universe and learn more about our own galactic home. Superclusters of galaxies represent some of the grandest and most massive structures in the universe. They consist of numerous galaxy clusters connected in vast networks that stretch hundreds of millions of light-years. These systems form under the influence of gravity and are key components of the large-scale structure of the cosmos. One of the most well-known superclusters is Laniakea, which includes our local group of galaxies. Laniakea spans 520 million light-years and contains about 100,000 galaxies. Discovered in 2014, its name, which means immeasurable heavens in Hawaiian, symbolizes its vast size and significance in the cosmic scale. Within Laniakea is the Virgo supercluster, which consists of thousands of galaxies and has a diameter of about 110 million light-years. It is one of the most thoroughly studied regions of space due to its relative proximity to Earth. Typically, superclusters contain numerous galaxy clusters. One of the densest is the Coma cluster, located in the Virgo supercluster, approximately 320 million light-years from Earth and containing over 1,000 galaxies. It spans about 20 million light-years and serves as a vivid example of how galaxies can cluster under gravitational forces. Another impressive supercluster is the Shapley supercluster, situated about 650 million light-years away, comprising thousands of galaxies grouped into several clusters and with a size of around 500 million light-years. The Shapley supercluster is one of the most massive structures known. These constructions are crucial for our understanding of cosmic processes. They provide insights into the early universe and its evolution over time, showcase the grandeur of cosmic structures, and open new horizons for research and discovery. How are these grand scales related to the concept of the cosmic web? The cosmic web is a term used to describe the large-scale structure of the universe, where galaxies and their clusters are distributed like nodes and threads in a vast web. This grand system, visible on the largest scales, results from the gravitational interaction of matter and dark matter, forming complex and extensive structures. According to cosmological modeling, over 60% of the hydrogen formed after the Big Bang collapsed to create a layer that then fragmented into cosmic filaments. These filaments connect galaxies and supply them with gas for growth and star formation. The main components of the cosmic web are filaments, nodes, and voids. There are two primary types of filaments, cold and hot. Cold filaments contain gas at relatively low temperatures, which promotes the formation of new stars. Hot filaments, on the other hand, are filled with high-energy gas heated to millions of degrees, which slows down star formation but significantly affects the dynamics of galaxies. According to a study published in Nature Astronomy *, astronomers have recently obtained a direct image of a section of the vast cosmic web structure previously hidden in a very distant part of the universe. Previously, scientists used the Keck Observatory in Hawaii to get an indirect image of this area billions of light-years away from Earth about 8 years ago, utilizing the light from a nearby quasar. Now, astronomers have managed to capture a direct image of cosmic web filaments located 10 to 12 billion light-years away, using background light filtering from the solar system and our galaxy. As a result, they captured the light of the most intense emission in the cosmic filament region, gaseous hydrogen. This area was previously hidden from astronomers because it lies much further in the darkest corner of the universe, where it was not illuminated by galaxy clusters or quasars. Consequently, astronomers have created a three-dimensional image of this very distant region of the web. One of the most impressive examples of filaments is the CFA-2 Great Wall, discovered in 1989. This structure spans about 500 million light-years and consists of numerous galaxy clusters connected by filaments. The Hercules Corona Borealis Great Wall, discovered in 2013, stretches an incredible 10 billion light-years and is one of the largest known structures in the universe. Voids, which fill the space between filaments and nodes, also play an important role. These areas are characterized by extremely low galaxy density and can span hundreds of millions of light-years. This complex network formed under the influence of gravitational forces acting on ordinary and dark matter since the Big Bang. Dark matter is a mysterious component of the universe that, despite being invisible, plays a crucial role in the formation of galaxies and large-scale cosmic structures. Although its nature remains unknown, scientists estimate that it constitutes about 27% of the universe's mass-energy content. Dark matter interacts with ordinary matter through gravity, but does not emit, absorb, or reflect light, making it invisible to traditional astronomical observation methods. The primary evidence for its existence emerged in the mid-20th century when astronomers noticed that the orbital speeds of stars in galaxies did not match the expected values based on the visible mass of these stellar systems. Galaxies were rotating faster than could be explained by visible matter alone, suggesting the presence of additional unseen mass. Dark matter forms gravitational frameworks around which ordinary matter accumulates, creating galaxies and their clusters. These frameworks are invisible halos that contain most of the mass. For example, in a typical galaxy, dark matter may be 10 times more massive than all visible stars and gas combined. In the Milky Way, the dark matter halo extends about 300,000 light-years, significantly exceeding the diameter of the visible part of the galaxy. How does dark matter influence galaxy formation? When the universe was younger and composed of hot plasma, it began to create gravitational wells. These wells became centers where ordinary matter accumulated, cooled, and formed the first stars and galaxies. Without dark matter, the process of galaxy formation would have been much slower and less efficient. Dark matter also affects the cosmic microwave background, CMB, which is the residual radiation from the Big Bang. Fluctuations in this radiation indicate the presence and distribution of dark matter in the early universe. CMB studies conducted with space telescopes like Planck have provided crucial data on its quantity and distribution. To further understand its nature, scientists conduct various experiments both in space and on Earth. They use detectors placed deep underground to catch rare interactions between dark matter particles and ordinary matter. Additionally, particle accelerators like the Large Hadron Collider, LHC, are used to create and study particles that might constitute dark matter. Thus, dark matter remains one of the most enigmatic and fundamental components of the universe. Its role in galaxy formation and large-scale structures is key to our understanding of the cosmos. Ongoing research and observations continue to provide more data, bringing us closer to unraveling this great cosmic mystery. What do we know about the elusive nature of dark energy? Dark energy is another mysterious component of the universe that, despite its invisibility, has a profound effect on its behavior. While dark matter is responsible for the formation of galaxies and large-scale structures, dark energy is responsible for the accelerated expansion of the universe. Scientists believe it accounts for about 68% of the total mass energy of the universe, making it the dominant component. Hints of dark energy's existence emerged in the late 1990s when two independent groups of astronomers studying type Ia supernovae discovered that the universe is expanding at an accelerating rate. This discovery contradicted the prevailing theories that predicted the expansion should slow down due to gravity. Instead, the observation suggested that some unknown force is pushing galaxies apart, causing the accelerated expansion. The rate of the universe's expansion is determined by the Hubble constant, which is currently estimated to be about 70 km/s/mpc, kilometers per second per megaparsec. However, this rate has not been constant throughout the history of the universe. Before the discovery of dark energy, it was assumed that gravity was slowing down the expansion. However, observations show that about 5 billion years ago, the expansion began to accelerate, indicating the predominant influence of dark energy. The mechanism of its action remains one of the biggest mysteries in modern cosmology. One leading hypothesis is the cosmological constant, proposed by Albert Einstein in 1917 within his general theory of relativity. Alternative hypotheses include the theory of quintessence, which posits the existence of a dynamic scalar field affecting the rate of the universe's expansion. Unlike the cosmological constant, quintessence can vary over time and space, leading to a more complex model of the universe's evolution. The influence of dark energy on the structure of the cosmos is evident when observing large-scale structures such as superclusters of galaxies and the cosmic web. Dark energy stretches space, causing distances between galaxies and clusters to increase. In the future, if current trends continue, star systems will continue to drift apart, and the universe will become increasingly sparse. Various observational methods are used to study dark energy, including mapping large-scale cosmic structures, studying the cosmic microwave background radiation, and investigating type Ia supernovae. Space missions, such as the Planck satellite and the upcoming Euclid mission, provide more data, helping scientists understand the nature of this mysterious force. How is cosmological redshift related to the study of dark energy? Cosmological redshift is a phenomenon associated with the expansion of the universe, playing a crucial role in modern cosmology. As light from distant galaxies and other cosmic objects travels toward us, its waves are stretched due to the expanding space. This results in an increase in wavelength and a shift of the light toward the red part of the spectrum. This effect is called redshift and is an important tool for studying the universe. The first scientist to discover redshift was the astronomer Edwin Hubble. In 1929, he observed that the light from distant galaxies was shifted toward the red part of the spectrum, and that the extent of this shift was directly proportional to their distance from Earth. This discovery laid the foundation for Hubble's law, which states that the rate at which galaxies are receding is proportional to their distance from us. Hubble's law is expressed by the formula V equals sign shx d, where v is the recessional velocity, d is the distance to the galaxy, and h0 is the Hubble constant, which is currently estimated to be around 70 km/s/mpc. Redshift is classified by the magnitude z, which indicates how much the wavelength of light has changed. If lambda is the observed wavelength and L0 is the original wavelength, then z equals sign lambda LO L0. For example, if z equals sign 1, it means that the wavelength has doubled. Cosmological redshift provides valuable information about the structure and evolution of the universe. It allows scientists to measure distances to distant galaxies and study their speeds, helping to determine the rate of the universe's expansion at different epochs. For instance, studying galaxies with high values of Z, such as Z equals sign 6 or higher, provides a glimpse into the early stages of the cosmos when the universe was less than 1 billion years old. Moreover, Redshift is used to create three-dimensional maps of galaxy distribution. Modern sky surveys, such as the Sloan Digital Sky Survey, SDSS, collect data on millions of galaxies and their redshifts, creating maps that display the large-scale structure of the universe. Interestingly, redshift is not limited to galaxies. It is also observed in the emission of cosmic microwave background, CMB radiation, which is a remnant of the Big Bang. It has a redshift of about Z equals sign 1100, corresponding to a time when the universe was about 380,000 years old. Cosmological redshift also plays an important role in calibrating cosmic distances. Type Ia supernovae, used as standard candles, allow for the measurement of distances to distant galaxies and the estimation of their redshifts. How are measurements of distances to distant galaxies using Type Ia supernovae related to determining the age of the universe? One of the primary methods for accurately estimating the age of the universe is the study of cosmic microwave background, CMB, radiation. This radiation is a relic of the Big Bang, preserved to this day and permeating all of space. Cosmic microwave background radiation was first detected in 1965 by Arno Penzias and Robert Wilson. It has a temperature of about 2.7 Kelvin and is distributed across the entire sky. Interestingly, this discovery was made by accident. The scientists used a microwave telescope and consistently detected an additional signal that did not disappear regardless of where they pointed the antenna. Initially, they suspected the signal might be due to a malfunction of the telescope or even pigeon droppings on the antenna. However, they later realized they were the first to detect cosmic microwave background radiation, the existence of which had been predicted by Big Bang theory. For their discovery, Penzias and Wilson used the 15-meter Holmdel horn antenna, which subsequently became famous for this significant finding. They were awarded the Nobel Prize for their achievement. This information is adapted from the conversation under a Creative Commons license. Modern space missions, such as the Planck Space Telescope, have provided the most detailed maps of the CMB, allowing scientists to make precise measurements of its characteristics. The Planck data, published in 2018, indicated that the age of the universe is approximately 13.8 billion years. This result is based on measurements of small temperature fluctuations in the CMB, which reflect the density and composition of the early universe. One of the key parameters used to determine the age of the universe is the omega parameter, which characterizes the density of various components of the universe: ordinary matter, dark matter, and dark energy. According to Planck data, the overall density of the universe is close to the critical density, omega-1, indicating a flat geometry of the universe. Additional methods used to estimate the age of the universe include observations of star clusters and white dwarfs. For example, measurements of the age of the oldest star clusters, such as globular clusters, suggest an age of about 13 billion years, consistent with estimates from the CMB. Studies of white dwarfs, the final stages of stellar evolution, also support these estimates. How does the age of the universe relate to its evolution? Observations show that within a few 100 million years after the Big Bang, the first stars and galaxies began to form. The period known as the reionization epoch occurred about 13 billion years ago, when ultraviolet radiation from the first stars and galaxies ionized hydrogen in the intergalactic space. The age of the universe, as determined from cosmic microwave background observations, is approximately 13.8 billion years. This result is based on data about temperature fluctuations in the CMB, matter density, and the rate of expansion of the universe. Ongoing improvements in observational methods and analysis continue to refine these estimates, bringing us closer to understanding the origin and evolution of our cosmos. The evolution of the universe is a remarkable story, encompassing a series of key stages and events, each contributing to the formation of the present cosmic structure. The initial state of the universe after the Big Bang was characterized by extremely high temperatures and densities. During the first trillionth of a second, the universe underwent a period of inflation, expanding at an incredible rate and growing in size by several orders of magnitude. This stage contributed to making the space more homogeneous and isotropic. Within seconds after the Big Bang, the temperature decreased to a level where elementary particles, such as protons and neutrons, began to form. About 3 minutes later, nucleosynthesis occurred, resulting in the formation of the first light elements: hydrogen, helium, and lithium. Hydrogen made up about 75% of the mass, and helium about 25%. Approximately 380,000 years after the Big Bang, the temperature dropped to about 3,000 Kelvin, allowing electrons to combine with nuclei to form neutral atoms. This process, known as recombination, made the universe transparent to light, which we observe today as the CMB. The next key stage in the universe's evolution is the era of dark ages, which lasted until the formation of the first stars and galaxies. Within a few 100 million years after the Big Bang, the first stars began to form, ionizing the surrounding hydrogen and initiating the epoch of reionization. This process ended around 1 billion years later. The first galaxies and clusters began to form within the first few billion years after the Big Bang. Gravitational interactions between dark matter and ordinary matter led to the formation of large structures such as galaxies and galaxy clusters. The Milky Way began forming about 10 billion years ago. Around 4.6 billion years ago, the solar system, including Earth, formed. Conditions on our planet became favorable for the emergence of life, with the first microorganisms appearing around 3.8 billion years ago. The development of life on Earth led to the evolution of complex organisms, including humans, who appeared about 200,000 years ago. The future of the cosmos remains an active area of research and speculation. Possible scenarios include the Big Rip, where accelerated expansion could lead to the destruction of all structures in the universe, or heat death, where the universe reaches a state of maximum entropy and ceases to support any processes. Inflation theory, proposed in the early 1980s, represents one of the most significant achievements in modern cosmology. This concept was developed to explain some mysterious aspects of the early universe, such as the uniformity and isotropy of the cosmic microwave background, CMB radiation, the flatness of the universe, and the absence of magnetic monopoles. According to the inflationary model, the universe underwent an extremely rapid period of exponential expansion in the first trillionth of a second after the Big Bang. This period allowed the universe to expand by many orders of magnitude, smoothing out any initial inhomogeneities and creating conditions for the formation of the large-scale structures we see today. The inflationary model proposes that during this brief time, the universe expanded by a factor of 10 circumflex 26. This process can be compared to inflating a small balloon to the size of a galaxy in a fraction of a second. How is this possible? One key aspect of the theory is the existence of an inflaton field that provided the energy for this extreme expansion. The inflaton field had a high energy density and exerted negative pressure, causing exponential expansion. Why is inflation theory so important? First of all, it explains why the universe appears so homogeneous and isotropic on large scales. Without it, any initial inhomogeneity or density fluctuation could have led to a much greater variation in temperatures and densities across different parts of the universe. Inflation smoothed out these inhomogeneities, providing a uniform distribution of matter and energy. Moreover, inflation explains why the universe is so flat. At the moment of the Big Bang, the universe could have had any geometric curvature. However, inflation expanded it so greatly that any initial curvature became nearly imperceptible. And today, we observe a universe that appears flat on large scales. The inflationary model also predicts the presence of initial quantum fluctuations that became seeds for the formation of galaxies and other large structures. During inflationary expansion, these fluctuations were stretched to cosmological scales, creating small density inhomogeneities that later led to gravitational collapse and galaxy formation. One of the first direct confirmations of the theory came from observations of the cosmic microwave background radiation by the COBE, Cosmic Background Explorer satellite, in 1992. These observations showed that the temperature of the CMB has small fluctuations consistent with the predictions of the inflationary model. Later missions, such as WMAP, Wilkinson Microwave Anisotropy Probe, and Planck, provided even more precise data confirming this model. The inflationary model also solved the problem of magnetic monopoles, hypothetical particles predicted by some theoretical models. In its absence, magnetic monopoles would have had to exist in large numbers, but inflation diluted their concentration to the point where they are practically undetectable. However, despite the successes of the concept, unresolved questions remain. For example, the nature of the inflaton field and the mechanisms that led to its end are still not fully understood. Some alternative models, such as eternal inflation and the multiverse, offer new avenues for research, but also raise new questions. This theory plays a key role in our understanding of the early stages of the universe's expansion. It explains the uniformity and flatness of the cosmos, as well as the origin of large-scale structures. How is the formation of the first stars and galaxies related to the early phases of the universe's expansion? The emergence of the first stars and galaxies represents a crucial stage in the evolution of the universe. This period, known as the Cosmic Dawn, marks the end of the Dark Ages and the beginning of the appearance of the first sources of light. The first stars, or population 3 stars, formed approximately 200 million years after the Big Bang. These stars were significantly more massive and hotter than modern stars. They were composed primarily of hydrogen and helium since heavier elements had not yet been synthesized. These stars could have masses ranging from several tens to hundreds of solar masses, and their lifespans were short, only a few million years. The development of the first stars began with the cooling and contraction of gas clouds. Gravity played a key role, causing the gas clouds to collapse and form dense cores that eventually became stars. How exactly did this process occur? Gravitational instabilities in the primordial gas clouds led to the formation of dense regions that continued to collapse under their own gravity. These regions gradually heated up, and when the temperature reached several million degrees Kelvin, thermonuclear reactions began, converting hydrogen into helium. Thus, the first stars were born. The appearance of the first stars had a significant impact on the surrounding environment. Their powerful ultraviolet radiation and strong stellar winds began ionizing the surrounding hydrogen. This process lasted for hundreds of millions of years and eventually led to the complete ionization of the intergalactic medium. The formation of the first galaxies began around 500 million years after the Big Bang. Galaxies formed in regions where the density of dark matter was higher, creating gravitational anchors that ordinary matter gravitated toward. The primordial galaxies were small and unstable, frequently colliding and merging with each other to form larger structures. The process of galaxy mergers played a key role in their evolution. For example, the Milky Way, one of the largest galaxies in our local group, formed through numerous mergers of smaller galaxies. How often did such mergers occur, and how did they influence the structure of galaxies? Approximately 1 billion years after the Big Bang, galaxies began to take on more organized shapes, such as spiral and elliptical forms. This process was accompanied by active star formation and the formation of the first supermassive black holes in the centers of galaxies. One of the key discoveries was the identification of galaxies that formed stars at an extremely high rate. These galaxies, known as starburst galaxies, produce stars hundreds of times faster than modern systems. This discovery allowed for a better understanding of the mechanisms of star formation and the role of galaxies in the evolution of the universe. Supernovae are also among the most powerful and dramatic events in the cosmos. These catastrophic explosions occur at the end of the life cycle of massive stars, leading to the release of enormous amounts of energy and matter into the surrounding space. Understanding the processes associated with supernovae is crucial for cosmology and the chemical evolution of galaxies. Supernovae are classified into two main types, Y and II. Type 1 supernovae occur in binary star systems, where one of the stars is a white dwarf that accretes matter from its companion until it reaches a critical mass, triggering a collapse and explosion. Type 2 supernovae occur when a massive star, having exhausted its nuclear fuel, collapses under its own gravity, leading to the explosion of its outer layers. What makes these events so significant for cosmology? First, supernovae play a key role in the chemical evolution of galaxies. During a supernova explosion, heavy elements such as carbon, oxygen, iron, and gold are synthesized and ejected into space. These elements become the building blocks for new stars, planets, and even life. For example, the iron in our blood and the calcium in our bones were created in the hearts of ancient stars and ejected into space by supernovae billions of years ago. An intriguing question is, can supernovae actually influence the emergence of life? Some scientists suggest that supernova explosions might have played a role in the formation of complex organic molecules in interstellar clouds, which in turn could have influenced the emergence of life on planets. These processes are still the subject of active research. Supernovae also serve as important tools for measuring cosmic distances. Moreover, supernovae play a role in the dynamics of galaxies. Supernova explosions create shockwaves that can compress surrounding gas clouds, initiating new cycles of star formation. These explosions can also affect the evolution of galactic disks and lead to the ejection of gas from galaxies, impacting their further evolution. One of the most famous examples of a supernova is SN 1987A, which exploded in the Large Magellanic Cloud in 1987. This event provided scientists with a unique opportunity to observe and study a supernova in detail. SN 1987A helped confirm many theoretical models and provided new data on the processes occurring during and after the explosion. Observations of supernovae are also closely linked to the search for neutrinos. Supernova explosions produce vast amounts of neutrinos, which can be detected by special detectors on Earth. These observations help scientists better understand the mechanisms of supernova explosions and the properties of neutrinos, which play an important role in fundamental physics. These powerful events continue to be the subject of active research, opening new horizons in our understanding of the cosmos and its evolution. Black holes are among the most mysterious and exotic objects in the universe. These regions of space-time with such a strong gravitational field that neither light nor matter can escape play a crucial role in cosmology and the evolution of galaxies. The concept of a black hole was first proposed by German scientist Karl Schwarzschild. According to his theory, a black hole can form at any point in space when a spherical object reaches what is known as the gravitational radius. Black holes can be classified into several types depending on their mass and origin. Primordial black holes, which could have formed shortly after the Big Bang, may range in mass from just a few grams to millions of solar masses. Supermassive black holes, which can reach billions of solar masses, are found at the centers of most large galaxies, including our own Milky Way. One key question is, how do these giants form? It is believed that supermassive black holes form through the mergers of smaller black holes and the accretion of vast amounts of gas. For example, the black hole at the center of our galaxy, Sagittarius A*, has a mass of about 4 million solar masses and likely formed through mergers and accretion over billions of years. Black holes play a central role in the evolution of galaxies. Their powerful gravitational pull influences the movement of stars and gas, shaping the structure of galactic nuclei. Active galactic nuclei, AGN, fueled by the accretion of matter onto supermassive black holes, can emit enormous amounts of energy in the form of light, X-rays, and radio waves. These emissions can significantly impact star formation processes in galaxies by heating and expelling surrounding gas. For example, quasar 3C273, one of the first discovered, is located about 2.4 billion light-years from Earth and emits energy equivalent to 1 trillion suns. How do such objects affect their surrounding environment? The intense radiation and powerful jets resulting from the accretion of matter onto a black hole can prevent further star formation in galaxies, thus regulating their evolution. Another aspect that greatly interests scientists is the collisions and mergers of black holes. These events produce gravitational waves, which can be detected by instruments like LIGO and Virgo. For instance, in 2015, LIGO detected gravitational waves caused by the merger of two black holes with masses of about 29 and 36 solar masses. This discovery confirmed key predictions of general relativity and provided a new tool for studying the universe. Black holes may also play an important role in the formation of relativistic jets, streams of particles moving at nearly the speed of light. These jets can extend thousands of light-years from the centers of galaxies and influence the intergalactic medium by injecting energy and matter into the surrounding space. Additionally, there is a hypothesis that entire planets and even alien colonies might exist inside black holes. According to Professor Vyacheslav Dokuchayev, a researcher at the Russian Academy of Sciences Institute for Nuclear Research, certain conditions in the centers of some black holes might create a region where space and time could exist. In such a structure, bodies including photons, particles, and planets could orbit around the central singularity. The singularity of a black hole is the central region where space and time become infinite. Black holes remain critical objects for understanding the structure and evolution of galaxies, as well as for exploring the fundamental laws of physics. Exoplanets, or planets orbiting other stars, have also become a focus of intense interest for scientists seeking signs of life in other parts of the universe. The first exoplanet was discovered in 1992, and since then the number of known exoplanets has significantly increased. As of 2024, astronomers have discovered more than 5,000, using various methods such as the transit method and radial velocity method. The transit method is based on observing starlight that temporarily dims when a planet passes in front of its star. This method has allowed the discovery of thousands of exoplanets, including many potentially habitable worlds. One of the key tasks is to find planets in the habitable zone, where conditions might be suitable for the existence of liquid water, a key ingredient for life as we know it. Interestingly, many are located in these zones, which increases the likelihood of finding life beyond Earth. For example, the exoplanet Kepler 452b, located in the habitable zone of a star similar to our Sun, has a radius 60% larger than Earth's and possibly a rocky surface. The next step in their study is the examination of their atmospheres. This is an important stage because an atmosphere can contain biomarkers, chemical substances that may indicate the presence of life. Using spectroscopy, specialists can analyze the composition of exoplanet atmospheres, identifying the presence of water, oxygen, methane, and other molecules. The detection of significant amounts of oxygen and methane in an exoplanet's atmosphere could indicate biological activity. Missions such as NASA's TESS, Transiting Exoplanet Survey Satellite, and ESA's PLATO, Planetary Transits and Oscillations of Stars, continue to expand our catalogue of exoplanets and provide new data for analysis. They are aimed at finding transiting exoplanets and studying their characteristics in search of potentially habitable worlds. Additionally, the Breakthrough Listen project, funded by Yuri Milner and supported by Stephen Hawking, uses radio telescopes to search for signals from extraterrestrial civilizations. This program aims to scan millions of nearby stars and galaxies for radio signals that could indicate a technologically advanced civilization. But what exactly could have prompted NASA to hold an emergency press conference and make such an important announcement? As previously reported by NV, the American Space Agency, NASA, held an emergency press conference at its headquarters in Washington. During the event, NASA representatives announced the most significant discovery in the history of the search for extraterrestrial life. 7 exoplanets were found orbiting a single star, TRAPPIST-1. Theoretically, they may have conditions that, from the perspective of modern science, are suitable for life. The star TRAPPIST-1 is located 39 light-years from Earth. It is much smaller than the Sun, approximately 12 times smaller, and its temperature is significantly lower. The discovered exoplanets are located close enough to each other for their gravitational fields to interact. This allowed scientists to estimate the planets' masses. The smallest has a mass of 0.4 times that of Earth, while the largest is 1.4 times that of Earth. According to preliminary observations, The planets in the habitable zone have water and oxygen. According to current scientific understanding, these are key factors for the emergence of life. Do these exoplanets have names? During the press conference, one of the scientists from the NASA working group that made the discovery joked that since the star's name, Trappist, refers to a type of Belgian beer, they wanted to name the planets after different types of Belgian beer. But a final decision has not yet been made. The study of exoplanets and the search for life beyond Earth remain one of the most exciting fields of modern science. The discovery of new worlds, the analysis of their atmospheres, and the study of potentially habitable zones open up new horizons for humanity and the possibility of answering the question, are we alone in the universe? Modern methods and tools for observing space have significantly expanded our ability to study the universe. One of the primary observation methods is the use of ground-based optical telescopes. Telescopes like the Keck Observatory in Hawaii and the Very Large Telescope, VLT, in Chile, are equipped with adaptive optics, which compensates for distortions caused by the Earth's atmosphere. This allows for clear images of distant galaxies, stars, and planets. For example, the VLT, with its 8.2-meter mirrors, can observe objects with a resolution of up to 0.05 arcseconds, enabling detailed views of exoplanet and satellite surfaces. In addition to optical telescopes, radio observatories play a crucial role. Instruments like the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, allow the study of cold objects, such as molecular clouds where stars and planets are formed. ALMA consists of 66 antennas that work together to create high-resolution images. The launch of space telescopes has ushered in a new era in astronomy. The Hubble Space Telescope, launched in 1990, has provided us with stunning images of distant galaxies, nebulae, and star clusters. Hubble operates in the visible, ultraviolet, and near-infrared wavelengths, allowing it to observe objects across various wavelengths. The recently launched James Webb Space Telescope, JWST, has become the new flagship of space astronomy. This telescope, with its 6.5-meter mirror and a suite of highly sensitive instruments, operates in the infrared range, allowing it to peer through dust and gas clouds that obscure many cosmic objects from visible light observations. JWST has already begun providing data on exoplanet atmospheres and distant galaxies, helping scientists study processes occurring in the early universe. An intriguing question is, what other secrets will JWST reveal? This telescope is capable of observing objects up to 13.6 billion light-years away, enabling us to glimpse the earliest epochs of galaxy and star system formation. In addition to optical and infrared telescopes, scientists use X-ray and gamma-ray observatories to study high-energy processes in the universe. The Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope provide data on extreme objects like black holes, neutron stars, and supernova remnants. For example, Chandra's observations have helped detect hot gas emitting in the X-ray range around black holes and quasars, allowing for a better understanding of accretion processes and the dynamics of these objects. Additionally, scientists are actively developing and using gravitational wave detectors such as LIGO and Virgo. Space missions like the Hubble and James Webb Space Telescope, JWST, have become crucial milestones in our understanding of the universe. These telescopes have provided scientists with incredible data and images, significantly expanding our knowledge of space. The Hubble telescope, named after astronomer Edwin Hubble, was launched in 1990. It orbits at a low Earth orbit at an altitude of about 547 kilometers and is equipped with a 2.4-meter mirror. Since its launch, Hubble has provided over 1.4 million observations, which have been used in more than 18,000 scientific papers. One of Hubble's most famous achievements was determining the age of the universe, about 13.8 billion years. This was achieved through observations of star clusters and variable stars, allowing scientists to better understand the rate of the universe's expansion. Hubble also played a key role in the study of exoplanets. In 2014, Hubble detected water vapor in the atmosphere of exoplanet HAT P11b, located about 124 light-years from Earth. This breakthrough demonstrated that even relatively small telescopes can provide important data on the composition of exoplanet atmospheres. Another major achievement of Hubble was its deep space observations. The Hubble Deep Field, created in 1995, revealed thousands of distant galaxies, many of which are over 10 billion light-years away. The James Webb Space Telescope, launched in December 2021, represents the next step in space astronomy. It orbits around the Lagrange point L2, about 1.5 million kilometers from Earth. With its 6.5-meter mirror and highly sensitive infrared instruments, JWST can peer deeper into space and study colder and darker objects that are invisible to Hubble. One of JWST's key successes was its first image of the SMACS 0723 field, which showed thousands of galaxies up to 13 billion light-years away. This image became the deepest and most detailed view of the universe to date. JWST has also made significant contributions to the study of exoplanet atmospheres. For example, it detected carbon dioxide in the atmosphere of WASP-39b, located about 700 light-years from Earth. JWST is also exploring protoplanetary disks, regions where new stars and planets are forming. Its observations have helped reveal the structure and composition of such disks, providing valuable information about star formation processes. Additionally, JWST can study galaxies in the early stages of their formation, when the universe was only a few hundred million years old. Space missions are not limited to Hubble and JWST. Many other telescopes and probes have made significant contributions to our understanding of space. For example, the Kepler Space Telescope, launched in 2009, discovered over 2,600 exoplanets, including many potentially habitable worlds. Its data has formed the basis for further studies of exoplanets and their atmospheres. The Cassini Space Probe, which explored Saturn and its moons from 2004 to 2017, provided stunning images and data about Saturn's rings and moons. One of Cassini's most significant discoveries was the detection of water geysers on Enceladus, which indicate the presence of a subsurface ocean potentially suitable for life. The New Horizons space probe, launched in 2006, reached Pluto in 2015 and provided the first detailed images of this distant dwarf planet. New Horizons also continues its journey through the Kuiper Belt, exploring other objects in this remote region of the solar system. Space missions continue to open new horizons and provide vital data for scientific research. In the future, even more powerful telescopes and probes are planned, such as the Nancy Grace Roman Space Telescope, which will study dark energy and exoplanets, and the ESA's JUICE mission, which will head to Jupiter and its icy moons. How might future space research and missions influence our understanding of hypotheses like the multiverse theory? Theories of the multiverse represent one of the most exciting and controversial hypotheses of modern science. They suggest that our universe is not the only one, but that there are many other universes, each of which may have its own physical laws, constants, and even dimensions of time and space. One of the first and most well-known multiverse theories is the inflationary model, proposed in the 1980s by Alan Guth. According to this theory, during the early phase of cosmic inflation, different regions of space-time could have expanded at different rates, creating multiple separate universes. These bubble universes may have different physical properties and laws. In one universe, one force may dominate, while in another, a completely different one. Another important version is quantum mechanics and its Everett interpretation, also known as the many worlds theory. This hypothesis suggests that every quantum event creates multiple parallel universes where all possible outcomes of that event are realized. Interestingly, if the multiverse theory is correct, the number of such universes could be astronomically large. According to some estimates, the number of possible universes could reach 10,500. This incredible number underscores the scale and diversity of possible realities that may exist beyond our observable universe. There is also string theory, which suggests that our universe may be just one of many within the string multiverse. In this concept, universes may exist in different dimensions hidden from our perception. String theory predicts the existence of additional dimensions that may be hidden or compacted at a scale inaccessible to our observations. The question that remains open is how we can test the hypothesis of the existence of multiple universes. One possible approach is to study the cosmic microwave background, CMB, for anomalies that might indicate interactions between our universe and others. However, such evidence remains elusive and requires further investigation. It is also worth mentioning that these theories raise many philosophical questions. If there is an infinite number of universes, each with different parameters, what does this mean for our understanding of reality? How does this affect the concepts of free will and determinism? Although direct evidence of the existence of multiple universes has yet to be found, ongoing research and observations may one day shed light on this mystery and revolutionize our understanding of the cosmos and our place within it. Quantum mechanics and cosmology are two fundamental pillars of modern physics that, despite differences in scale, are closely interconnected and complement each other. Quantum mechanics describes the behavior of particles at the subatomic level, while cosmology studies the universe as a whole, its origin, structure, and evolution. The combination of these two fields of knowledge opens new perspectives for understanding the deepest questions about the nature of reality. One of the key areas where quantum mechanics and cosmology intersect is the Big Bang theory. According to quantum theory, fluctuations in the early universe could have caused variations in matter density, which eventually led to the formation of galaxies and other large structures. These quantum fluctuations, which occurred within the first fractions of a second after the Big Bang, are recorded in the cosmic microwave background, CMB, which serves as a snapshot of the early universe. It is interesting to note that quantum effects may also play a role in the process of cosmic inflation, the theory that proposes the universe underwent a period of exponential expansion immediately after the Big Bang. Quantum mechanics helps explain how small, random quantum fluctuations could have been stretched to vast scales, creating density perturbations that became the seeds for future galaxies. Another area where quantum mechanics is important to cosmology is in understanding the nature of dark matter. The quantum version of particles offers many candidates for dark matter, such as axions, or weakly interacting massive particles, WIMPs. These hypothetical particles could explain anomalies in the movement of galaxies and galaxy clusters. The question that remains open is how quantum phenomena might influence cosmological processes on scales beyond our current science. One such unresolved problem is gravitational singularity, the quantum nature of which is still a subject of active research. Quantum mechanics also plays a role in studying black holes and their interaction with the surrounding environment. For example, the theory of black hole evaporation proposed by Stephen Hawking is based on quantum effects. According to this theory, black holes can emit radiation, known as Hawking radiation, gradually losing mass and eventually evaporating. This discovery suggests that quantum phenomena can have a significant impact on the evolution of objects on scales comparable to cosmological ones. It is also crucial for understanding fundamental questions about the nature of time and space. In string theory, one of the most promising attempts to unify quantum mechanics and general relativity, time and space are considered quantum objects that can experience fluctuations on very small scales. This could lead to new insights into the origin and evolution of the universe. One of the most exciting aspects of studying quantum mechanics and cosmology is the possibility of the existence of parallel universes. The many worlds theory suggests that every quantum process may create a separate universe with different outcomes. These two branches of science, though different in their scale and approaches, mutually enrich each other, providing deep insights into fundamental questions about the origin, structure, and evolution of the cosmos. With further research and new discoveries, we will get closer to unraveling the mysteries hidden in the deepest recesses of time and space. Philosophical aspects of cosmology extend beyond pure scientific inquiry and touch on fundamental questions about the nature of reality, the origin and fate of the universe, and humanity's place in the cosmos. Cosmological studies, including theories about the beginning and future of the universe, the multiverse, dark matter, and dark energy, inevitably provoke reflections on profound issues of existence and consciousness. One of the most significant philosophical questions in cosmology concerns the nature of reality itself. If our universe is just one of an infinite number of others, What is the true nature of existence? If there are countless universes with different physical laws and constants, what does this say about reality as commonly understood? These questions highlight the relativity and subjectivity of our perception of the world. An intriguing question arises. What if our entire universe is merely one of countless experiments in a cosmic laboratory? This philosophical aspect is closely related to the anthropic principle, which questions the uniqueness of our existence and leads to reflections on the role of the observer on a cosmic scale. Cosmological research also raises questions about finitude and infinity. Modern theories about an expanding universe, along with hypotheses of a possible Big Rip or Big Crunch, pose the question of whether the universe has a beginning and an end, or if it exists in some form of cyclical time. These reflections lead to philosophical discussions about the nature of time and its connection with space. On the other hand, if the universe has no end and time, as well as space, are infinite, it poses questions about infinity and how human consciousness can comprehend such concepts. Infinity creates paradoxes and contradictions in human thinking, forcing us to reconsider traditional notions of time and space. Additionally, cosmology raises questions about free will and determinism. If the universe adheres to strict physical laws, does free will exist, or are all events predetermined? In the context of quantum mechanics and the multiverse theory, this question becomes even more complex. In some interpretations of quantum mechanics, each possible outcome of an event could lead to the creation of a new universe, where all possible variations of events are realized. Another important philosophical aspect of cosmology concerns the meaning of life and human uniqueness. If our universe is not unique and there are others, what is humanity's role in this vast cosmic reality? This prompts contemplation about the significance of human life, its purpose, and its place in the broader cosmos. Philosophical reflections on the future of the universe also play a crucial role. The question of what will happen to the universe in the distant future, whether it will continue to expand indefinitely or eventually contract into a singularity, holds both scientific and philosophical significance. The anthropic principle is a philosophical concept that asserts that the universe has the physical and cosmological parameters necessary for the existence of life, particularly intelligent beings capable of observing and exploring it. In cosmology, the anthropic principle is significant because it helps explain some of the mysterious aspects of our universe and its laws. There are two main versions of the anthropic principle, the weak and the strong. The weak anthropic principle states that the laws of physics and the parameters of the universe could vary, but we observe this particular universe because otherwise we could not exist and make observations. This statement seems trivial, but it prompts consideration of why physical constants, such as the gravitational constant or the speed of light, have the specific values that allow the formation of stars, planets, and ultimately life. The strong anthropic principle, on the other hand, suggests that the universe must have parameters that inevitably lead to the emergence of intelligent beings. This version of the principle provokes more debate and philosophical reflection, as it implies that our existence is not a random outcome of evolution, but an inevitable consequence of cosmological laws. For instance, one of the most well-known manifestations of the anthropic principle is the fine-tuning of fundamental physical constants. If the gravitational constant was slightly higher or lower, stars could not sustain themselves, and planets capable of supporting life would not form. Similarly, if the strong nuclear force were a bit stronger, hydrogen would have completely converted to helium in the early stages of the universe, leading to a lack of water, a key element for life. Is our universe one of many where different physical laws and constants apply? The multiverse theory, as mentioned earlier, offers an explanation for the anthropic principle. If there is an infinite number of universes with varying parameters, it is quite possible that only some of them have conditions suitable for life. In this case, the anthropic principle simply explains why we find ourselves in such a universe. However, the principle also has its limitations. For example, it cannot explain why specific physical constants and natural laws have their particular values. It indicates that our existence is consistent with the observable universe, but does not answer why these laws are as they are. Cosmologists and philosophers continue to debate the significance of the anthropic principle and its role in science. Some view it as a useful tool for explaining the fine-tuning of the universe, while others see it as a philosophical postulate with no scientific value. It is also interesting to consider the anthropic principle in light of current observational data. For instance, recent measurements of the cosmic microwave background, CMB, and the distribution of galaxies in space confirm that our universe possesses the properties necessary for sustaining life. The anthropic principle in cosmology raises important questions about the nature of the universe and its fundamental laws. Whether one accepts the weak or strong version of the principle, it challenges us to rethink our place in the cosmos and consider the possibility that our existence is not merely a coincidence but the result of the fine-tuning of the entire universe. Nonetheless, alternative theories offer different perspectives on the origin and evolution of the universe. The Big Bounce hypothesis is an alternative theory to the standard cosmological model, which posits that the universe began with the Big Bang. Unlike the classical model that suggests a one-time expansion of the universe, the Big Bounce hypothesis proposes a cyclical scenario where the universe undergoes infinite phases of expansion and contraction. According to this theory, the current phase of the universe's expansion is a result of a previous contraction cycle. At the point when it reaches a certain minimum size or state of maximum density, a so-called bounce occurs, after which a new expansion cycle begins. One of the key questions of this hypothesis is what causes the cessation of contraction and initiates a new cycle. Answers to this question involve complex processes related to quantum gravity, which remain a subject of theoretical research. What do the numbers say? According to current observations, the universe has been expanding for about 13.8 billion years. The Big Bounce theory suggests that there could have been another universe before this, which contracted for a similar amount of time. In this case, a complete cycle of expansion and contraction might take approximately 28 billion years, providing a unique perspective on time in the cosmological scale. One aspect of the Big Bounce hypothesis is its impact on the understanding of entropy. According to the second law of thermodynamics, entropy, or disorder, in a closed system should increase over time. However, if the universe is constantly expanding and contracting, the question arises, what happens to entropy in each cycle? Some theorists suggest that at the moment of the bounce, there is a reset, allowing each new cycle to start with a low level of disorder. Others argue that entropy accumulates and is carried over from one cycle to another, potentially leading to interesting consequences for the structure and evolution of the universe in the long term. The Big Bounce hypothesis also requires a re-evaluation of the cosmological singularity. In the classical Big Bang model, it is assumed that the universe originated from a singularity, a point of infinite density and temperature. However, in the Big Bounce model, a singularity may not exist, as the universe never contracts to a state of infinite density. Instead, the minimum size and density of the universe are determined by quantum effects that prevent complete contraction and initiate expansion. Many aspects of the Big Bounce hypothesis remain speculative and require further research and confirmation through observations. Nonetheless, this theory provides an intriguing perspective on the possible future of the universe and its cyclical nature. If the Big Bounce truly exists, it could mean that the universe we observe is just one in an infinite series of universes, and our experience of time and space is merely a temporary state in the endless cycle of cosmic evolution. How does gravity, as a fundamental force, influence the formation and evolution of structures in the universe? Since the Big Bang, when all matter was evenly distributed, gravity has been shaping the complex hierarchy of structures we observe today, ranging from planetary systems to galaxies and their clusters. In light of the new hypothesis proposed by Professor Erik Verlinde from the University of Amsterdam in 2010, gravity might be viewed not as a fundamental force of nature, but as a result of changes in the information stored in the structure of space and time. Verlinde argues that the attraction between bodies arises from differences in entropy density in space, leading to its increase and the transition of the system to a more probable macroscopic state. In the earliest stages of the universe, a few 100,000 years after the Big Bang, The cosmic microwave background, CMB, emerged as residual radiation from that time. These initial density fluctuations observable in the CMB became the seeds for the subsequent formation of galaxies and their clusters. The density differences were minimal, around 0.001%, but it was through gravity that these small fluctuations began to grow, leading to the formation of large cosmic structures. What if the gravitational force were even slightly weaker or stronger? Even a small change in its value would drastically alter the development of the universe. If gravity were weaker, matter might not have been able to coalesce into stars and galaxies, leaving the universe as a sparse expanse. Conversely, if it were stronger, matter would have collapsed too quickly, leading to an early collapse and a shortened lifespan for stars. Today, we observe gravity continuing to shape the universe. On the scale of galaxies, it is responsible for keeping stars in orbit around the galactic center. For example, in the Milky Way, the gravity of the central black hole holds billions of stars in their orbits. Black holes typically occupy central positions in galaxies and exert immense gravitational influence, leading to the formation of complex structures like spiral arms. On the scale of clusters, gravity acts as glue, holding together dozens and sometimes hundreds of galaxies in giant structures. Clusters of galaxies can have masses ranging from 10 circumflex 14 to 10 circumflex 15 solar masses. Gravity is also the reason for the formation of large voids in space. These, known as cosmic voids, are enormous regions of space almost devoid of galaxies. The size of such voids can reach hundreds of millions of light-years. Between these voids lies the cosmic web, a network of galaxies and their clusters formed by gravitational attraction. Without gravity, the universe could not possess the complexity and diversity we see today. Thus, Verlin's hypothesis offers a new perspective on understanding gravity and its role in shaping the universe. In the scale of the universe, energy and matter are not just related but are distributed according to fascinating and complex patterns. The interaction between them forms everything we observe and even what remains hidden from our eyes. The main components of the universe can be categorized into three types: ordinary, baryonic matter, dark matter, and dark energy. Despite the vast amount of visible matter that makes up stars, planets, and galaxies, its share in the total mass energy of the universe is surprisingly small. A much larger portion of the universe is occupied by dark matter, which does not interact with light and does not emit it. The term dark matter was first used in 1906 in the works of French mathematician Henri Poincaré, where he described peculiarities in the distribution of stellar velocities around the center of our galaxy. Dark matter is responsible for the gravitational binding of galaxies and galaxy clusters, and its presence is only apparent through gravitational effects. Astronomers have completed one of the most extensive studies of matter distribution in the universe. By studying gravitational lensing, scientists have measured the amount of mass and substance in different regions of the universe. The map is based on data collected from dark energy surveys and the South Pole Telescope. Lead author Sukhdeep Singh states that the new map of the universe's matter is important for many reasons. The most mysterious component is dark energy. Its density is about 7 times 10 circumflex minus 30 GCM3, which is billions of times smaller than the density of a hydrogen atom. But what will happen if the distribution of matter and energy in space changes? Is it possible that with the continued expansion of the universe, energy will be distributed in such a way that less and less matter remains in compact structures like galaxies and stars? The future of the universe is one of the most intriguing questions in modern cosmology, which scientists are trying to unravel based on current observations and theories. To understand what may await us ahead, it is necessary to consider key factors influencing its development, including the role of dark energy, the curvature of space, matter density, and other cosmological parameters. One theory about the future of the universe suggests its infinite expansion. If dark energy continues to dominate, the cosmos will expand faster and faster, and in billions of years, this could lead to a scenario known as the Big Rip. In this scenario, accelerated expansion will cause all structures, including galaxies, stars, planets, and even atoms, to be torn apart. However, This scenario depends on the properties of dark energy, which are still not fully understood. Another possible scenario is the Big Freeze. In this model, the universe continues to expand, but at a constant rate or with deceleration, and eventually, stars and galaxies will begin to die as the fuel for nuclear reactions is depleted. In trillions of years, the universe will be left with only cold, dead stars, black holes, and rare elementary particles scattered in an infinitely thin space. There is also the possibility of a big crunch, where if the density of matter in space exceeds a critical value, gravity will start to slow down the expansion, and then the universe will begin to contract until it reaches a state of high density and temperature similar to that at the moment of the Big Bang. When the universe contracts 20 times and becomes 100 times smaller than it is now, it will be a single enormous galaxy. The temperature of the cosmic microwave background will reach 274 K, and ice on Earth-like planets will start to melt. Further contraction will lead to the cosmic background radiation outshining even the central star of planetary systems, burning out the last traces of life on planets. Soon after, stars and planets themselves will evaporate or be torn apart. The state of the universe will resemble what it was in its early moments. Subsequent events will resemble the early moments, but played in reverse. Atoms decay into atomic nuclei and electrons. Radiation dominates. Then atomic nuclei decay into protons and neutrons, and then protons and neutrons decay into individual quarks, leading to a great unification. At this moment, as in the Big Bang, the known laws of physics cease to apply, and the further fate of the universe becomes unpredictable. Regardless of which scenario turns out to be true, we can only continue to explore, observe, and learn as we approach the unraveling of the greatest mystery of our existence. What cosmological models help us understand the structure and evolution of the universe more deeply, explaining phenomena such as the expansion of the universe and the distribution of matter? Cosmological models are various theories and mathematical descriptions that scientists use to understand the structure and evolution of the universe. They help explain observed phenomena such as the expansion of the universe, the distribution of matter, the cosmic microwave background, and more. Among the many proposed hypotheses and theories, several models stand out as fundamental in modern cosmology. One of the most well-known models is the LCDM, Lambda Cold Dark Matter model, which is considered standard in cosmology. LCDM successfully describes many cosmological observations, including the structure of the cosmic microwave background and the large-scale structure of the universe. Another model to mention is the quintessence model, which offers an alternative explanation for dark energy. Unlike the LCDM model, where dark energy is treated as a cosmological constant, lambda, the quintessence model describes dark energy as a dynamic field that evolves over time. This approach allows for possible variations in the rate of the universe's expansion during different epochs of its evolution. Equally important is the inflationary model of the universe proposed in the 1980s, which explains the early phases of its development. It successfully addresses several problems, such as the flatness and homogeneity of the universe, and explains the origin of initial quantum fluctuations that later led to the formation of large cosmic structures. However, there are also more exotic models, such as cyclic models, including the Big Bounce model. Unlike LCDM, these models suggest that the universe does not have a beginning or an end, but instead undergoes infinite cycles of expansion and contraction. In the cyclic model, after each contraction phase, the universe bounces back and starts a new cycle of expansion. An intriguing alternative is the model of multiverses, where our universe might be just one of many existing in different dimensions or parallel realities. In this concept, the multiverse could contain various physical laws and parameters, potentially explaining the uniqueness of our universe. By comparing different cosmological models, scientists conduct complex observations and experiments to test the predictions of each. For example, observations of the cosmic microwave background using the WMAP and Planck satellites have provided crucial data for testing the LCDM model, showing its high degree of agreement with observed data. People gaze into the infinite depths of space, wondering how many astonishing things are happening out there that they have no idea about. For example, many know that comets have tails. But have you ever heard of a tailed planet? Mercury is the smallest planet in the solar system. It is 18 times lighter than Earth, and its diameter is barely 2/5 the size of Earth. Surface temperatures vary more than on any other planet in the solar system, from -173 degrees Celsius at night to 427 degrees Celsius during the day. This is because it has almost no atmosphere to retain heat. Despite being closer to the Sun than other planets, Mercury is not the hottest planet. Why is this planet considered tailed? Mercury trails a stream of sodium atoms that the solar wind blows off its surface. From a distance, it looks like the tail characteristic of comets. It is not easy to see. It requires a long exposure photograph using a telescope and a special filter. It's also important to choose the right time. The tail is brightest within 16 days of the planet's perihelion. Another interesting fact is Saturn, which has a hexagonal storm. It was first discovered in 1981 by NASA's Voyager spacecraft. Later, in 2006, the Cassini spacecraft provided more detailed images and data. It turned out that the storm is about 300 kilometers high, 29,000 kilometers wide, and possibly consists of atmospheric gases moving at about 320 kilometers per h. The sides of the hexagon are about 14,500 kilometers long, which is 2,000 kilometers more than the diameter of Earth. It also changes color depending on the season on Saturn. In summer, it turns golden, and in winter, it turns blue. Another noteworthy planet in the solar system is Neptune. It was discovered in 1846. It was the first planet discovered through mathematics. Astronomers noticed that Uranus deviated from its predicted orbit, which allowed them to hypothesize the existence of another planet and then find it. Neptune is so far away that it can only be seen with optical instruments. As it is the farthest from the Sun, it also has the longest orbital period. A year there lasts 164.8 Earth years. That's why, since its discovery, it has only completed one orbit around the Sun, which happened in 2011. Now you know a bit more about the universe. Cosmological research is impossible without significant technical advancements, which have formed the basis for many discoveries that have changed our understanding of the cosmos and its evolution. One of the key technological breakthroughs is the development and launch of powerful space telescopes, such as the Hubble Space Telescope and the James Webb Space Telescope, JWST. Another major achievement has been the advancement of radio telescopes and interferometry. The Atacama Large Millimeter Submillimeter Array, ALMA, and the Very Large Array, VLA, have enabled the study of molecular clouds where stars and planets form, as well as the investigation of structures around black holes and in the centers of active galaxies. ALMA, consisting of 66 highly sensitive antennas, provides images with an angular resolution of up to 0.01 arcseconds. Laser interferometry technology, implemented in the LIGO, Laser Interferometer Gravitational Wave Observatory project, played a crucial role in confirming the existence of gravitational waves predicted by Einstein. A significant achievement in computational technology is the creation of supercomputers, such as Summit and Fugaku, which are used for modeling complex cosmological processes. Noteworthy are also the advancements in spectroscopy and sky surveys. Projects like the Sloan Digital Sky Survey, SDSS, create maps of the universe with unprecedented precision, covering millions of galaxies at distances of billions of light years. An important advancement has been the development of cryogenic detectors and instruments for measuring the relic radiation. Experiments like Planck have accurately measured the anisotropies of the cosmic microwave background, providing information about the early universe and its age. The technological advancements of recent decades have greatly expanded the possibilities of cosmological research, enabling scientists to address fundamental questions about the origin, structure, and fate of the universe. These technologies continue to evolve, opening new horizons for future discoveries. Cosmology, as a science at the intersection of various disciplines, has undergone significant changes since its inception. Modern achievements and discoveries have given us a deeper understanding of how the universe is structured, its origin, and its future, but many questions remain unanswered. Research continues, and scientists hope that future missions will shed light on the nature of these mysterious components. Our current knowledge of the universe has already allowed us to make predictions about its future. The future promises to be as exciting as the past. With the advancement of technology, we can expect new discoveries and theories that will transform our understanding of the universe. In the coming decades, missions are expected to explore exoplanet atmospheres in more detail and search for signs of life. What if, in the vast expanses of space, there are galaxies that are invisible to our eyes and instruments? Such structures, composed entirely of mysterious dark matter, may exist right now, yet their nature remains hidden from us. Modern scientific tools allow us to look further into space, but dark galaxies continue to elude us, as if concealed in the shadows of the universe. Meanwhile, distant exoplanets may harbor oceans filled with liquid water. Water is known to be a key element for sustaining life. But what conditions are necessary for its existence beyond Earth? Can we hope to find extraterrestrial life when considering the factors influencing the formation of such worlds? Or are we in for disappointment? Cosmology faces even greater mysteries, such as the existence of quantum wormholes connecting different parts of space-time. If these phenomena are real, they could fundamentally alter our understanding of the universe. But how might they interact with the more familiar structures around us? And what laws govern such portals into the unknown? The hypothesis of dark galaxies is one of the most intriguing assumptions in modern astrophysics. A dark galaxy is a hypothetical object of galactic scale that contains an extremely small number of stars, or is entirely devoid of them, which is the basis for its name. These galaxies are held together by dark matter, and may also contain gas and dust. To date, the existence of dark galaxies remains unconfirmed, despite the presence of potential candidates. What secrets do these potential dark galaxy candidates hold? And can they alter our understanding of the structure and evolution of the universe? E04502958 is an unusual quasar around which no galaxy has been detected. There is a suggestion that this object may represent a dark galaxy where the quasar has become active. However, subsequent observations indicate that a normal galaxy is likely present nearby. Virgohi 21 was discovered in February 2005 and became the first convincing candidate for being a true dark galaxy. The object was identified during the study of hydrogen, Hi radio emission, at a wavelength of 21 centimeters. Its dynamics appear to be inconsistent with the predictions of modified Newtonian dynamics, MOND. Some researchers have hypothesized that Virgohi 21 may be a dark galaxy and represent a tidal tail of the nearby galaxy M99, which is experiencing gravitational disturbances while entering the Virgo cluster. Dragonfly 44, discovered in 2015, stands out for its low brightness. It emits only 1% of the light that the Milky Way emits. This galaxy has an extremely low density. Its diameter is about 60,000 light-years, and the number of stars within it is less than 1 billion. In a study published in late August 2016, scientists calculated the mass of Dragonfly 44 by examining the velocity of stars and their clusters within the galaxy. The mass was found to be 1 trillion solar masses, which is close to the mass of the Milky Way, but only 0.01% of this mass is attributed to stars and gas. Thus, astronomers concluded that the galaxy is almost entirely composed of dark matter. However, new research from 2020 disproved this hypothesis. But if dark galaxies are indeed real, what other hidden structures or phenomena might exist in the depths of space? Can we hope to find similarly mysterious aquatic worlds on distant exoplanets that could offer new opportunities for discovering life? Water is a key element associated with the potential for life, and its presence on exoplanets is one of the main objectives of astronomical research. As the number of known exoplanets beyond our solar system increases, new horizons emerge in understanding their diversity and potential to support life. Authors of a recent study analyzed 17 Earth-like exoplanets, suggesting that vast oceans may exist on their surfaces, hidden beneath an icy crust. All these exoplanets are believed by scientists to possess geological activity and to be capable of cryovolcanism, implying the ejection of heated material to significant heights. 2 of these planets are located close enough to Earth that astronomers may be able to observe geysers on their surfaces using modern telescopes in the future. Over the past few decades, astronomers have described numerous exoplanets that vary in size, density, and distance from their stars. These planets can be divided into gas giants, such as hot Jupiters and cold Neptunes, as well as rocky exoplanets comparable to Earth. The latter are of particular interest, as they may harbor extraterrestrial life, especially those exoplanets that have oceans, planets containing significant volumes of liquid water. In a study published in the Astrophysical Journal, scientists assessed the internal heating and ocean depths on 17 icy worlds. The modeling showed that all of them are capable of containing large volumes of liquid water, consistent with their average temperatures and densities. However, new data indicate that the average temperature on these planets is 16 degrees lower than previously estimated. In particular, the exoplanets Proxima Centauri b and LHS 1140b, which have thin layers of ice, may exhibit cryovolcanic activity that exceeds that of Europa by hundreds of times. Additionally, research conducted with the James Webb Space Telescope, JWST, confirmed the existence of exoplanet K218b, which is likely to have liquid oceans. Data showing the presence of carbon-containing molecules in its atmosphere, such as methane and carbon dioxide, suggest the possibility of life. This exoplanet, 8.6 times more massive than Earth, lies within the habitable zone of its star, located 120 light-years away. Studies of K218b are intriguing because they may indicate the presence of conditions suitable for life. However, scientists caution against premature conclusions about the existence of life on this planet. Given its large size and structure, the planet may have high-pressure ice mantles and temperatures that are not conducive to life. Further research using the mid-infrared instrument, MIRI, aboard JWST, is expected to provide scientists with more information about the atmosphere of K218b and its potential to support life. Exoplanet research, as recent discoveries have shown, opens new opportunities for the search for extraterrestrial life, highlighting the importance of considering the diversity of exoplanetary systems in astronomical studies. How might the creation of a holographic wormhole using a quantum computer open new horizons for exploring oceans on exoplanets and understanding their potential habitability? Researchers have made a significant breakthrough in quantum physics by sending a signal through an artificially created wormhole for the first time in a laboratory setting. This wormhole, described by Albert Einstein and Nathan Rosen in 1935, acts as a tunnel connecting 2 points in space by utilizing additional dimensions. The foundation for this wormhole's creation lies in holograms made from quantum bits of information, or qubits, stored in tiny superconducting circuits. The researchers manipulated the qubits to transmit information through the wormhole. A team led by Maria Spiropoulou from the California Institute of Technology implemented a new wormhole teleportation protocol using Google's quantum computer, a device named Sycamore, located at Google Quantum AI in Santa Barbara, California. This experiment emerged from a quantum gravity experiment on a chip, allowing Spiropoulou and her team to outpace competitors from IBM and Quantinuum. This experiment supports the holographic principle, which unifies 2 pillars of fundamental physics: quantum mechanics and general relativity. Since the 1930s, physicists have struggled to reconcile these 2 disparate theories. The former explains the behavior of atoms and subatomic particles, while the latter describes how matter and energy warp space-time, creating gravity. The holographic principle, which gained popularity in the 1990s, suggests a mathematical equivalence or duality between 2 structures. Proponents of this principle argue that the flexible space-time continuum described by general relativity is in fact a quantum system of concealed particles. Space-time and gravity emerge from quantum effects. similar to how a three-dimensional hologram projects a two-dimensional pattern. Although discussions about wormholes began nearly a century ago, it took many years to develop the theory and the effort of an experimental team to create the first wormhole on a quantum computer. The experiment confirms that controllable quantum effects in a quantum computer can produce a phenomenon expected in relativity theory, a wormhole. However, we cannot observe this wormhole like an ordinary hologram. While it can be considered a fiber of real spacetime, as noted by co-author Daniel Jafferis from Harvard University, it is not part of the reality in which we live or the reality of the Sycamore computer. The holographic wormhole in the experiment consists of spacetime distinct from that of our own universe. The question of whether this indicates that the spacetime we inhabit is also holographic and formed from quantum bits remains open. Jafferis emphasizes that there is a possibility that gravity in our universe arises from quanta, akin to how this one-dimensional wormhole emerged from the Sycamore chip, though this has yet to be proven. Research into the holographic wormhole is rooted in two seemingly unrelated papers published in 1935, one by Einstein and Rosen, the ER paper, and the other involving Podolsky, the EPR paper. In the ER paper, Einstein and Rosen derived the possibility of wormholes, seeking to unify general relativity with a theory of everything that encompasses both spacetime and its dependent subatomic particles. They turned to elements of the fabric of spacetime found by Carl Schwarzschild in 1916, shortly after Einstein's publication, which showed that mass can gravitationally collapse to the point of becoming infinitely concentrated. The singularities discussed by Einstein and Rosen are now known as points that we cannot describe or see, as they are hidden at the center of a black hole. They represent a domain where a quantum theory of gravity is required. Einstein and Rosen proposed that Schwarzschild's equations could be used to connect elementary particles with general relativity by replacing singularities with new variables and describing them as bridges between different parts of space-time. Unfortunately, scientists did not initially pay attention to the phenomenon of quantum entanglement described in the EPR paper, which stated that measuring the state of one particle instantaneously affects the state of another, regardless of the distance between them. This spooky action at a distance, as Einstein referred to it, became crucial in understanding quantum mechanics and holographic theory. In the 1990s, physicists discovered that quantum entanglement could enable new types of computation, leading quantum gravity researchers to consider it as a potential source code for the spacetime hologram. In a 1994 paper, Leonard Susskind articulated the holographic principle, suggesting that the volume of spacetime described by general relativity is equivalent to quantum particles at its boundary. Juan Maldacina's work in 1997 corroborated this principle by demonstrating that anti-de Sitter ADS space is indeed a hologram. Compared to our universe, ADS space is filled with negative energy and possesses hyperbolic geometry. Maldacina showed that gravity within ADS space corresponds to the properties of a quantum system at its edge. Subsequently, when Maldacina explored his ADS CFT correspondence, he discovered that the entangled particles corresponded to a hologram featuring a pair of black holes linked by a wormhole. A decade later, he concluded that this discovery might indicate a more general correspondence between quantum entanglement and connections through wormholes. In electronic correspondence with Susskind, they speculated that the Einstein-Rosen bridge between black holes is created by EPR-like correlations, and that this duality might be more general than previously assumed. Research also indicates that wormholes may link entangled pairs of particles throughout the universe, forming spatial connections that record their shared history. When Jafferis learned about Maldacina's work, he realized that such a duality should allow for the creation of individual wormholes by adapting the entanglement pattern. Previously, it was thought that Einstein-Rosen wormholes would quickly collapse under gravitational influence, but Jafferis proposed that a connection could be stretched between two entangled particles, opening a wormhole between them. Together with graduate student Pin Gao and researcher Aaron Wall, they confirmed that linking two entangled particles allows for operations that can lead to the creation of a traversable wormhole. The experiment conducted by Jafferis, Gao, and Wall in 2016 opened new horizons in the study of holographic mechanics. Later, Maldacena and colleagues developed a framework demonstrating that a traversable wormhole can indeed be created, confirming that quantum systems can generate and manipulate such phenomena. But how might quantum wormholes influence our understanding of the universe as a whole? Could vacuum energy, one of the most mysterious forces operating on cosmic scales, be related to these phenomena and unveil the secrets of the universe's expansion? Vacuum energy is one of the most enigmatic aspects of modern cosmology. It represents the sum of the energies of the lowest energy states of all quantized fields present in the vacuum. This energy exhibits uniformity in space and constancy in time, and its density is considered a universal constant. The existence of vacuum energy has significant implications that can be observed in various phenomena, such as spontaneous emission, the Casimir effect, and the Lamb shift. It is also believed that vacuum energy influences the behavior of the universe on cosmological scales. One prominent example of the observable influence of vacuum energy is the Casimir effect, predicted in 1948 by Dutch physicists H. Casimir and D. Polder. They discovered that a tiny attractive force arises between closely spaced metallic plates, caused by the resonance of vacuum energy in the space between these plates. This phenomenon has been experimentally confirmed and indicates that vacuum energy is real in the same sense as familiar conceptual objects like electrons and magnetic fields. However, alternative explanations for the Casimir effect have also been proposed. Other predictions related to vacuum energy are harder to verify. Vacuum fluctuations are always generated in the form of pairs of particles and antiparticles. Physicist Stephen Hawking explained the mechanism of black hole evaporation through the creation of these virtual particles near the event horizon. If one particle of the pair falls into the black hole, the other particle becomes real and is emitted into space. This loss of mass and energy is cumulative, which over time can lead to the disappearance of the black hole. The time required for this process depends on the mass of the black hole and can reach around 10 circumflex 100 years for solar mass black holes. Vacuum energy also has important implications for physical cosmology. According to general relativity, energy is equivalent to mass, and therefore if vacuum energy truly exists, it must exert a gravitational influence. A non-zero vacuum energy is expected to contribute to the cosmological constant, which in turn affects the expansion of the universe. But if vacuum energy does indeed influence cosmic expansion and other structures in space, what unusual circumstances led to the formation of stars? And how did they affect the development of subsequent cosmic objects? The very first stars in the universe formed approximately 300,000 years after the Big Bang, which corresponds to around 13.5 billion years ago. A recent discovery made by scientists from France and Italy using the VLT ground telescope located in Chile pertains not to the stars themselves, but to their remnants. In the early universe, heavy elements, known to astronomers as metals, were quite rare. The first stars were almost entirely composed of hydrogen and helium and had low metallicity. Throughout their short lives, nuclear fusion reactions occurred in the cores of these stars, transforming hydrogen and helium into heavier elements. At the end of their life cycles, these stars exploded as supernovae, contributing to the spread of new elements into space, such as carbon, oxygen, and magnesium, which have been detected in the outer layers of stars. All the elements produced by the first stars became the foundation for the formation of the next generation of stars, leading to increased metallicity in later stars due to the presence of more heavy elements. Scientists believe that the cores of the very first stars also contained a small amount of iron. However, the supernova explosions that marked the end of their life cycles were less powerful than those of modern stars. As a result, iron and other heavy chemical elements did not disperse far into space. Nevertheless, carbon mixed with iron, left over from the explosions of the first stars, has been detected in distant gas clouds. Researchers managed to identify this carbon in 3 scattered gas clouds containing remnants of the first stars that vanished billions of years ago. Astronomers are confident that this discovery will help deepen our understanding of the nature of the early universe and the character of the first supernova explosions. To find chemical traces of the first stars, scientists analyzed the light from the brightest objects in the universe, quasars. These light sources are formed as supermassive black holes, consume vast amounts of matter in the active cores of galaxies. As light passes through gas clouds, different chemical elements absorb it at various wavelengths, allowing researchers to determine the composition of the gas cloud. The analysis revealed that the clouds contain very little iron and a lot of carbon and other heavy elements produced from the deaths of the first stars. Scientists now plan to continue searching for similar gas clouds to ascertain how many exist in the universe. But if these giant primordial stars left their mark in history, how did the two mysterious substances, dark matter and antimatter, interact in those distant times? And what influence did they have on the subsequent structure of the universe? Scientists have discovered antinuclei composed of antimatter particles that have the largest mass among all known. Physicists have been able to confirm some theories regarding the nature of antimatter through the detection of the heaviest antinuclei made up of exotic elementary particles. This new discovery may aid in the search for the mysterious particles that make up dark matter. The research findings were published in the journal Nature, as reported by Science Alert. What is antimatter? The existence of antimatter was first recognized by physicists in 1932 when the positron, or anti-electron, was discovered. Since then, scientists have established that all known fundamental particles have their counterparts in the form of antimatter particles, referred to as antiparticles. Antiparticles differ from ordinary matter particles in that they have an opposite electric charge. It is believed that equal amounts of matter and antimatter were created during the Big Bang, but very little antimatter remains in the universe today. Physicists have been trying to understand the reasons for this phenomenon for decades, proposing various hypotheses. One such hypothesis suggests that almost all of the antimatter from our universe resides in an anti-universe created during the Big Bang. Returning to the new discovery made by physicists at the Relativistic Heavy Ion Collider in Brookhaven, USA, scientists collided the nuclei of heavy chemical elements at very high speeds in the collider. During these collisions, hundreds of new particles are generated, which physicists can identify. Most of these particles are pions or pi mesons, which exist for only fractions of a second before rapidly decaying. However, during the new experiment, physicists managed to identify the heaviest antimatter particle. In nature, atomic nuclei consist of protons and neutrons, but physicists can create hypernuclei, in which neutrons are replaced with a heavier version called hyperons. As a result, physicists discovered the heaviest known hypernucleus of antimatter, or antihypernucleus, composed of an antiproton, two antineutrons, and an antihyperon. This antihypernucleus has been named antihyperhydrogen 4. Physicists were able to identify a total of 16 such antimatter particles. Comparing anti-hypernuclei to hypernuclei showed that they possess identical properties, instability, decay in approximately 1/10 of a nanosecond, and the same mass. This supports existing theories. How is antimatter related to dark matter? Antimatter may be linked to the mysterious substance known as dark matter, which is estimated to be about 5 times more abundant in the universe than ordinary matter, yet has never been directly observed. Some physicists believe that collisions of dark matter particles may produce ordinary matter and antimatter, particularly resulting in particles such as antihydrogen and antihelium. Antihelium has already been detected on the International Space Station, which may be associated with dark matter. Experiments like those conducted by the US physicists will help better understand how much antimatter is produced in collisions of ordinary matter particles. This could bring scientists closer to understanding what constitutes dark matter and ultimately allow for its direct detection. If dark matter and antimatter indeed have a key influence on the universe, is it possible that there are cosmic singularities, mysterious regions where gravitational forces are so immense that time and space could break down? What role might singularities play in these processes? The cosmological singularity is a proposed state of the universe at the moment of the Big Bang, characterized by infinitely high density and temperature of matter. This phenomenon is considered one of the examples of gravitational singularities predicted by general relativity, GR, and some other theories of gravity. In 1967, Stephen Hawking rigorously proved the inevitability of the emergence of a cosmological singularity when tracing back in time any solution of GR that describes the dynamics of the expanding universe. However, this proof is limited to the framework of classical GR and does not account for quantum effects. Hawking also emphasized that observational results support the assumption that the universe originated at a specific moment in time. However, the very moment of creation, that is, the singularity, does not obey known laws of physics. One of the problems associated with the cosmological singularity is the impossibility of simultaneously having infinite density and temperature. With infinite density, the measure of chaos approaches zero, which excludes the possibility of combining it with infinite temperature. The existence of the cosmological singularity is one of the most serious problems in physical cosmology, since any information about events after the singularity cannot provide insight into what happened before it. Attempts to resolve this problem are being pursued in several directions. Firstly, it is believed that quantum gravity could offer a description of the dynamics of the gravitational field free from singularities. Secondly, some researchers suggest that taking quantum effects into account in non-gravitational fields could violate the energy dominance condition on which Hawking's proof is based. Thirdly, there are modified theories of gravity in which singularity does not arise, as the extremely compressed matter begins to repel under the influence of gravitational forces, rather than attracting, as is assumed under singularity conditions. Another intriguing question is, what mechanisms, including gravitational lensing, can distort and amplify light traveling through cosmic spaces, and how do these processes unveil the mysteries of distant galaxies? Gravitational lensing is one of the most intriguing effects in the cosmos, resulting from the influence of large objects in the universe on light. However, this phenomenon can be caused not only by massive, but also by smaller cosmic bodies. The essence of the effect lies in the fact that light passing through another cosmic object on its way to an observer is distorted, altering the visibility of the light source. This distortion can be caused by stars or galaxies that the light from a more distant object passes through. There is also evidence that even small objects, such as planets, can cause lensing, although their impact is so minimal that it can only be detected using powerful telescopes. The discovery of the gravitational lensing effect was made possible only with the development of modern astronomy and the creation of advanced telescopes, which allowed scientists to observe and study this remarkable phenomenon. Light from distant objects such as quasars or galaxies is deflected as it passes through the gravitational field of another galaxy or star. This creates an effect similar to that of a lens, where the light is distorted and the shape of the light source changes. One of the most famous examples of gravitational lensing is the so-called Einstein ring. This effect occurs when the light from a distant object passes through a compact galaxy, becoming distorted and forming a circular shape. This phenomenon can be observed, for example, in the case of the galaxy cluster SDSS-J 1038 plus 4849, captured by the Hubble telescope. In this case, one galaxy acts as a lens for the light from another galaxy, creating the Einstein ring. Another variant of the gravitational lensing effect is the Einstein cross. It occurs when light passes through a spiral galaxy, creating an image reminiscent of a cross. This effect is also observed thanks to powerful optical telescopes such as the Herschel telescope, which in 2009 captured the object H142900028, a galaxy cluster that creates another Einstein ring. Gravitational lensing is a unique cosmic effect that allows us not only to study distant objects, but also to better understand the structure and interactions of various bodies in space. But if such forces can distort our view of the universe, what happens to objects that may simply disappear? Can an entire galaxy evaporate into the void of space if gravitational forces weaken? Although galaxies are considered some of the most massive and enduring structures in the universe, Even they cannot exist forever. Sooner or later, they face an end. But what could lead to the demise of such grand cosmic objects? American astrophysicist Paul Sutter from the Flatiron Institute in New York provided an answer to this question in an interview with Space.com. According to the scientist, the quickest end for a galaxy may come from the activation of the supermassive black hole located at the center of most galaxies. For example, at the center of the Milky Way lies the black hole Sagittarius A*, which has a mass exceeding 4.5 billion suns. But what happens if this monstrous force starts actively consuming matter? In that case, the black hole will begin heating the surrounding gas to temperatures exceeding 1 billion degrees, releasing an enormous amount of radiation. This radiation will not only overheat the supplies of interstellar gas, but will also halt the birth of new stars permanently, or for a very long time.